Hello. Good morning, everybody. Welcome back. Much to the disappointment of a few of you, I'm sure, I'm still alive. So the test will go on a week from this Thursday. I could take a few days off. It'll be all right. Yeah, you guys wouldn't like that, trust me. We can't cram the rest of this class into fewer days than I already have scheduled. Thank you for those that sent emails and been asking how I'm doing face-to-face. Means a lot. Everything went well. I have a new set of tattoos and Band-Aids. Right? Okay. Which they tell me eventually will, wear off, rub off. I get to take the Band-Aids off today. But there was immediate relief from my neurological symptoms because they injected lidocaine. Lidocaine cuts off any nerve sort of sensation or pain response. So I was like, oh, I can feel my fingers again, and it doesn't hurt to wiggle my fingers and stuff. So that was nice. The lidocaine kind of wears off after about 6 to 8 hours. And it takes a couple of weeks for the other medications that they put in, steroids that they put in there, to get into full effectiveness. But I can already feel the steroids working because it feels really hot in here to me. My other class said my face was red, but I think my hot flash is over. I told my wife we now have something in common, and she didn't think that was so she's having hot flashes too, but that's an age thing. Yeah, it went really well. I don't remember any of it, of the procedure. Last thing I remember is them telling me, okay, roll over on your face. After that, no memory. I asked the anesthesiologist, I said, are you going to give me the stuff that makes it so I don't remember? She's like, oh, yeah. Oh, yeah. I was like, yes. It's good stuff. I like not remembering things. Okay. Speaking of not remembering things, or not wanting to remember things, we were started on Kirchhoff's rules, right? This method of analysis for circuits when the circuits get more complicated than if you just had a whole bunch of capacitors or a whole bunch of resistors. The truth is that Kirchhoff's rules can be applied to any circuit. You can apply it to a simple circuit that consists only of resistors. It'll work just fine. The thing about Kirchhoff's rules is that they're required if you have a complex circuit, and especially for you right now, that means more than one battery in the circuit. And you might be sitting there going, well, why would you want one more battery? And I'll tell you at the end. But what I want to do is I want to draw a circuit right now that we're going to spend a little bit of time here analyzing. And when we get through this, so this is your example about how to use Kirchhoff's rules and how to problem solve on complex circuits. After that, we're going to move into household wiring a little bit and try to explain some of what's going on in your house, why the plugs are the way they are. And then we'll sort of finish up with some conceptual things. I'm in my lab get up today because I've had 4 hours of sleep in the last 24 hours, and putting on button-down shirt and real pants, it's too hard. I don't apologize. Have I asserted my dominance long enough in this class for you guys? Can I just do this for the rest of the semester? No.
That's most of us, though.
Sometimes I do walk into official meetings looking like this. If it's a lab day and the dean's called a meeting or the president's called a meeting, I just walk in like this. They don't blink anymore. They don't even register anymore, right? The first few times they're like, that's how I roll. All right, here is my circuit, or a circuit, not my circuit, circuit I was given. So we're going to have a resistor up here. I'm going to leave some room for drawing other things. This is a 30 ohm resistor sitting right there. And that's going to be connected to a 20 ohm resistor and a 21 ohm. Can I take the ohms off? Are you guys okay that if there's a number next to the thing, the unit is implied by the squiggles? Okay, it's going to make it a little bit cleaner. and then a 45 volt battery. All right, so I'll put volts on the battery just to make sure that we remember. So far so good, right? Nothing wrong with this circuit. Those resistors are what? How are they connected? They're in series with the battery. We're good to go. And this is where it all starts going wrong, because we're going to put another branch in this circuit coming down here. And we're going to put in an 80 volt battery and connect that to an 11 ohm resistor. So you look at this, and here's the problem, right? Like, if you take a look at the 11 ohm resistor, is it in series or in parallel with the 21 ohm resistor? I mean, it looks like it's parallel, right? Because there's a junction between it and between those two resistors. But the problem is now there's a 45 volt battery, right? You've been taught that we kind of do series and parallel things with respect to like the battery, right? Is it in series with the battery? Is it in parallel with the battery? Go as far away from the battery as possible to start simplifying your circuit, right? And so it seems like all of this is in reference to the battery or the voltage source. We've got two voltage sources in this problem. And so the 11 ohm is simultaneously parallel with the 2120, but it's also in series with the 80 and the 45 and what's happening with the 30, and right? Because I could draw a series circuit to the 30. Like, it just gets messy. And at some point, electrical engineers, people that deal with circuits, they just kind of give up on the whole series and parallel thing. And they start trusting Kirchhoff's rules. These rules that say batteries can only push so much charge through the circuit, and that must be conserved. A battery will push charge all the way around until it gets back to the battery. And when it gets to a junction, those charges will split up however they want, but eventually it's all got to come back to that battery, right? And then you have the loop rule, which says that the energy that those charges are given has to be consumed before they get back to the battery. Conservation of charge, conservation of energy, these are fundamental parts of how the universe works. And so we can take advantage of them to solve complicated problems like this one. We are going to simplify this circuit just slightly because there is a very obvious connection that we can fix, or at least make simpler. Which one?
The two resistors.
2 resistors in the middle, right? Those are definitely what? In series, aren't they? So if you can, if it's super obvious, simplify the circuit. But don't spend, like, even if you didn't do this step, it would still work. It's just, well, the math would be a little bit messier. So we're going to redraw this circuit with our 30 on the top. And then in the middle, we're going to have a 41. And then we're going to have the 45. Did I do that right? 20 plus 21 is 41, right? Yeah. And then we're going to have our 80 volt battery right down here. And we're going to have our 11, I keep drawing that one funny, 11 ohm resistor. Now, the 11 ohm I drew there, could I have drawn my 11 ohm right there? Sure, right? No problem. It's just, for whatever reason, I'm drawing it over there. Okay, so there is our circuit. And now we have to be able to apply both the junction rule and the loop rule. So I am going to make a little bit of, I'm going to try and fit it all on this slide. This could be dangerous. I'm just going to move those up so that they're kind of out of the way. And I think I've got enough room. Let's give this a shot. If not, I'll spill it over onto the other page. Okay, so junction rules. I'm going to label the two junctions. The only reason I am labeling these is so that we can talk about them together as a class. You really don't have to label your junctions and be as formal as I am. It's just it's handy if I can say, okay, let's go from A to B in the clockwise direction, right? Or B to A or whatever, right? It's different. It's just a reference point for you to latch your brain onto as I'm talking about the circuit, rather than me saying, well, to the left of the 40, right? That kind of stuff. But yeah, you don't really need to do that. It's just, it helps in communication a little bit. Okay, so to be able to apply a junction rule, we need to know what direction the currents are flowing in our circuit. Now, how do you know how many currents there are in your circuit? Look at a junction. How many wires are at junction A? There's 3, aren't there? How many wires are there at junction B? Also 3 wires. That means there is a minimum of 3 currents in this problem. Could be more, but there's definitely a minimum of 3 unique currents in this problem. You get to choose what direction those currents are flowing. You get to choose, unless the problem states otherwise. And spoiler alert on the exam, I stated the direction, because if you guys were all picking, then I'd have to solve the problem 30,000 different ways, right? So on the exams and in homework, oftentimes they'll say, assume the current is pointing this way. That's just trying to get it so that you get the same answer as the computer as far as a positive or negative sign is concerned. But in general, you can choose the directions you want the currents to be. If you choose the direction incorrectly, the only thing that'll happen is you will get a negative current. So if you get a negative current, all that means is that the direction you chose for your current was backwards. You still know the number. You still know the magnitude, which is what we want anyway. Okay? So please don't freak out on getting the direction correct unless the problem specifically says, assume the current does this, right? Okay, so we get to pick, and I'm going to pick for you, because that's what my notes say. There are 3 currents, and so that means there are 3 branches. Here's one branch going from A to B in the clockwise direction around the top of my circuit. I've got a current that begins at A, doesn't go anywhere, is all series connections until I get to B. Where's the second branch? Oh, from B down to A? Or from A to B on the downward portion? Doesn't matter. Going clockwise or counterclockwise. So that's another circuit current. And where's the third? Yeah, it's the middle one, right? So basically, we've got to pick directions for what these currents are doing. And what I'm going to do is I'm going to define current number 1. I'm just going to pick. Current number 1 is flowing clockwise from A to B through the top half of my circuit. I'm going to define current 2 as going counterclockwise through the bottom half, through the 80 volt side. And then I'm going to do current 3 in the middle branch, going from right to left. When I'm left on my own to just decide what directions the currents may be, I tend to follow what batteries are doing. I'll look at the voltage source, right? This 80 volt, and I'll usually match my current direction as whatever direction the battery's pointing. I don't know why I do that. It's just something, I guess, my brain said that was easier, and over time I learned that I made fewer mistakes if I do that. Again, you don't have to do that, right? It's just, for me, that's why I wrote I3 the way I did, right? I'm just following the 45 volt battery. And again, if I'm wrong about that, then what's going to happen? I'm just going to get a negative sign, and I'll know that I picked the direction wrong. It doesn't matter. Okay. So now that I've got my 3 currents picked, I can write down my junction rules. I'll write them down for both junctions, although you're going to see here I didn't need to do that. So at junction A, remember the rule is current in equals current out. So what currents are flowing into junction A? I have I3 going that way, I2 going down, and I1's going up. So what's flowing into junction A? It's just I3. Current in equals current out. So that must mean that I1 and I2 were both flowing out of that junction. Again, let's just look at it again. I3 was moving to the left into A, but then I1 was leaving up and I2 was leaving down, wasn't it? In equals out. Charge must be conserved. So that's what I wrote down there. Okay. Junction B, like I said, we'll do it, but you're going to find out I didn't need to. What's flowing into junction B? I2 and I1 are both coming in, and I3 is going out, right? So that equation looks like I1 plus I2 equals I3. And what are those two junction equations? They're identical, right? And that shouldn't be any surprise, because all three wires that were involved in junction A are also involved in junction B. If you have a more complicated circuit, there could be an I4 in here or something like that, right? Then it would be different. But this circuit is about as simple as we can get and still do Kirchhoff's laws. All right. So we've got our currents. We wrote down our junction rules. Now we have to do the loop rule. And for the loop rule, you again are free to choose the direction of the loops. But it can be a little bit difficult to identify how many loops there are in this circuit. A loop in a circuit would be like starting, say, at A, and then tracing a path back to A, completing that circle that is unique or different from another path that you could take in this circuit. So does anybody want to take a stab as to how many loops I have in this circuit? There are 3 loops in this circuit. Most people want to say 2, right? Because there's a loop like up here, isn't there? And that loop would be clockwise from A through B, through the middle, back to A. That's one loop. And where's the second loop? I'm using the wrong colors here. I want to do loops in green. Can you guys see the green okay? Okay. So loop 2 would be down here. Maybe B through A, back, right? So there's my bottom loop. But where's the third loop? It's the one that's around the outside. Okay? Quite often the one that everybody forgets. Right? So try not to forget the outside loop. Okay? So I usually draw like 1, 2, 3s with circles around them to identify that I've identified a loop. But it's not enough to identify the loop. You must identify or choose the loop direction. And again, this doesn't matter, like whether you're right or wrong about the direction. What matters is once you pick it, stick with it. Just like in 4A, when we defined a coordinate system, you had to make sure that the signs on the forces were correct, right? Here, once we pick it, we stick with it. So I'm going to do clockwise for loop number 1. I'm going to do counterclockwise for loop number 2. And it looks like I did clockwise for loop number 3. I try to put these little arrows on my loops to indicate what direction I am choosing that I want to go in this loop. So what we've done here in picking the currents and picking the loops is we've established a coordinate system for the circuit. We will now apply these conventions to that coordinate system, following these rules or conventions that are laid out to make sure that we stay consistent with our choices. What do I mean by that? Let's do loop number 1. So loop number 1, okay? You can start anywhere. it doesn't matter where you start on the loop. But if you start at A and you start going around the loop, where do you have to finish? Back at A, right? If you start at this 45-volt battery, that's fine. Just make sure you go around the loop that you specified and you make it back to the battery, okay? I'm going to start at A, and I'm going to come up. I'm going to pretend like I'm a charge moving through the circuit or an ant walking along the wire. I don't care. Whatever your image is in your brain. But the very first thing the charge hits is what? A 30 ohm resistor. Now, the loop rule is all about voltage. Remember? Okay? And so we're going to write down voltage for every single thing. If it's a resistor, we're going to write down I times R, Ohm's law. The voltage across the resistor is the current times the resistance. If it's a battery, we're just going to write down the battery voltage. Okay? However, we are coming at this 30 ohm resistor. And we got to come over here and we got to look at our conventions for resistors. So which way is the current flowing through the 30 ohm resistor? From left to right, isn't it? Right? Because I said the current is flowing around up from A across, right? Like that, right? So in this portion, it's flowing from left to right. You could say it's going in the clockwise direction if you wanted to. Okay? And what direction is our loop direction taking us? Same direction. If the loop and the current are the same direction through a resistor, what do we write down? Negative I times R. So what I'm going to write down is negative I1 times 30. Why 30? That was the resistance, right? If it was just labeled R1, you could just write R1 if you wanted to. All right. So we've walked along. We went through the 30. We're coming around. Now we're at B. Nothing's happening at B. We turn, and now we hit a 45-volt battery. What does our convention say for batteries? What's important about a battery? It's only the loop direction. It's not the current. It's only the loop direction. And if we go from a negative or small plate to a positive plate, big plate, what do we call it? Positive voltage. And is that what we're doing? Going through this battery, we go from a small to a big. I like to think of it as going the correct way through the battery. Maybe that's being a little bit voltagist of me, but it's supposed to go through a battery the right way. Okay, so since our loop direction and our battery direction are the same, I'm going to make that a positive 45 volts. All right, what's the next element that we run into as we work our way around our loop? Another resistor. And when we encounter a resistor, what are the two things we are comparing? Loop and current direction. The loop direction, clockwise or to the left. Current direction, also to the left, so it's negative IR, right? When loop and current are the same. And of course, I could have drawn this picture so loop and current were like that, right? Either way, if the loop and current are the same direction as chosen by you, then what do you call it? For a resistor? Negative. The reason it's negative is because it's a voltage drop. Resistors take up potential in a circuit. Make sure you get the right current, right? It's I3, it's not I1 anymore. We're in a different branch of the circuit. All right, and now we've started at A, we did the 30, we did the 45, we did the 41. Now we're back to A, so what do we write? Equals 0. Remember, the loop rule is currents, if you go around a loop, your voltages will add up to 0. Quick check. I've got a positive thing and two negative things, so this is a possibility. Right? If it was all positives or all negatives, I'd start to worry. It means I probably missed a direction somewhere. Like applying that, I didn't apply I chose something and then I didn't live by it. That's probably what happened. All right, Let's do loop number 2. Why don't you do loop number 2 right now in your notes, right? Just try to bang out loop number 2. Let me give you a hint. Start with 0 equals. It's so easy to forget that 0 equals that I like to put it on first, okay? So 0 equals, and then pick a place. Everybody start at A. Start at A and work your way around the loop in the counterclockwise direction. This will hopefully help you see where you are struggling or like not understanding like conventions and things. So don't be afraid to get it wrong. How are we doing? Like, are you lost? Were you able to get something down? Something. Not sure if it's right or wrong or that kind of stuff, right? Okay. Show your neighbor. Like, show them what you got. See where they got. Help them out if they're, not as far along as you and vice versa. Compare and contrast. Call me over if you're stuck, if both of you are stuck. What was that?
Do they do differential calculus for this stuff?
Differential equation? Yeah. Yeah, we haven't gotten there yet.
Oh, we will. Oh, okay. So we are going to.
Well, now that you mention it.
There's another integral problem. It's set up.
What's missing from this circuit that we have studied but haven't included here? Soon as you put a capacitor in here, it becomes a differential equation. All right. I wrote this down. I think it's correct. Check me. How did it go for you? Did you get the same? Were you able to do that by yourself, or did you need the help of the person next to you to just get everything ship-shape and Bristol faster? Yeah, it helps to be able to bounce these ideas off of each other, right? Show them what you got and why they got it and all that kind of stuff. So, but yeah, good if you can get it by yourself. Better if you can get it with help. All right. And of course, I can simplify these equations. I'll do that in a second. Let's do loop 3. Okay. And for loop 3, I'm going to start at A, and I'm going to go all the way around, right? Because I said loop 3 goes around in the clockwise direction. So I'm going to start at A. And I'm going to write this down. 30I1. I reversed. Sorry, I should write those the correct ways around. I1 times 30 minus I2 times 11 plus 80. All right. I'm going to tell you right now there's an error in there. Okay, good. Some of you were catching it as I did it. Where's the error? I211 is not correct. Now, is my plus 80 correct? No. I screwed up on both of those, didn't I? Okay. So on the exam, one way for me to see if you know about Kirchhoff's loop rule is to give you a circuit, give you the loops and the currents, and then give you an equation and say, correct this equation. Right? It's a little bit faster way without you having to set everything up to be able to see if you right. Or give you a series of equations and say, okay, which of these equations is incorrect and why? Right? So I did this. This time I made the mistakes on purpose, right? To just show you that there's a way of me evaluating what you know, right? That can sort of shortcut a lot of the setup, right? And get straight to the meat of, is this junction rule right? Is this equation right? Like I give you the whole picture. I give you all the loops. I give you all the current directions, right? So you want to be able to do a little bit of troubleshooting. So the I211 is positive. Why? So my loop's taking me down through 11, but I2 is going up through 11, right? So that means the loop and the current are opposites. So it's plus IR. And then the loop takes me backwards through the battery as I think about it, from the big to the small plate. And since it's backwards, I use negative. All right. What do we got? We have, and I will move this over to another page. Let's copy that and paste it right there. So those are the equations we came up with from this circuit analysis, right? This has all been visualization and strategize. This has all been the setting up of the problem. What have we set up? We've set up a bunch of equations. We have 5. How many unknowns do we have? 3. What are our 3 unknowns? I1, I2, and I3, right? So what we've got to do is we've got to pick 3 of these equations. Minimum. If there's 3 unknowns, we need a minimum of 3 equations, right? To be able to solve this. So I am going to not pick this equation. Why am I not going to pick that equation? Because the other one's exactly the same. So I am going to pick I3 equals I1 plus I2. And then over here, over time, you get a little bit used to what you should pick and what you should not pick, or like what's easier mathematically or any of that kind of stuff. As long as you pick equations that have all 3 of your things in it, you're going to be okay. It can be a little bit easier, a little bit harder to solve for, depending. But I'm gonna pick the first one, and I'm going to clean it up a little bit. Negative 30 I1 And then I'm going to write negative 41i3. There's a reason I'm doing it this way. Plus 45. I'm actually going to clean that up one more step, but I'm going to get there in a minute. And then I'm going to do loop 3. So this is loop 1, and this is loop 3's equation. I'm avoiding loop 2. I don't know why. I don't like it. Negative 30. I remember now. Minus 11i2. I'm putting the numbers in front because I'm used to having the number and then the unknown thing, right? Minus 80. Okay, so what? No, it's not. Positive. Thank you. All right, I'm actually going to write these up on the abomination because I'm going to want to reference them. And I'm going to write them kind of a little bit funny here. I'm going to write I1 plus I2 minus I3 equals 0. What did I just do there? I put all the unknowns on one side and I put the constant on the other side, right? And I'm going to do this for the rest of these equations. So this is going to be negative 30 I1, negative 41 I3 equals, is it negative 45? It's positive, but I move it over to the other side so it becomes negative 45. And then it's going to be negative 30 I1 plus 11 I3 equals positive 80, right? I2. Thank you. See? See what happens? Right on the abomination, it all goes wrong. The reason I've written it this way is to make the subsequent math I'm about to do a little bit easier. Okay? The reason I picked loop 1 and loop 3 is they both had 30 I1 in them, didn't they? Okay, which is suggesting to me I might be able to do some substitution and elimination of I1 and then just have I2s and 3s maybe left behind and figure out some way of doing it. The brute force method of solving this problem, you've actually done. This was problem number, was it problem number 1 on your lab? Did I give you this problem? Maybe I'm remembering. Did I change that? Where's my lab number 1? Did you have 3 equations with 3 unknowns? Oh, no, I gave you vector stuff instead, didn't I? Never mind. Never mind. I gave you vector stuff instead. I gave you 2 vector problems instead of an algebra problem. Vectors are a little bit more important. Okay, so the brute force way of doing this can be long, tedious, fraught with danger. It's like an algebra jungle here, okay? So, don't do it. But wait, Mr. Balogh, I've got to be able to do my homework. Yes, you do. However, the internet knows how to do problems like this. So I want to show you how you do this. This is one of the greatest things about the internet that there ever was. And I know you can't see it yet. Let me see if the right link comes up. Okay. I'll do Google instead. Okay. Let me show you what I've got. Okay. I went to Google and I typed in linear solver. That's all I typed in. Okay? Because this is a set of linear equations. Math 17, anybody? Okay. If you haven't had Math 17, don't panic. You're not supposed to know about it. But this is a set of linear equations. And linear algebra is the mathematics of solving many equations for many unknowns. It's called matrix algebra sometimes because you use these matrices to figure stuff out. It's actually really powerful. It's the one math class I never went to that I wish I did. I didn't go because the teacher was a jerk. And that's on me. I should have put that aside and just gone and learned it because I've used linear algebra a lot. Linear algebra and differential equations are like the go-to things for me in physics. So we're going to go to the linear solver. And you get to this page, the University of Côte d'Azur. That's an island somewhere, I'm sure. Okay, so we're going to use the matrix method. Individual method. Okay, you'll know it's right when it looks like this. Now, you can do this in a calculator. You can do this on Wolfram Alpha. ChatGPT could probably do it. Okay, but I like this one because it seems really straightforward to me. It just gives me boxes and I type things into boxes, right? I don't really need to get them in any other format. But you notice how there's one unknown plus the second unknown plus the third unknown equals something? That's what I've tried to do when I rewrote my equations up here. That's what I tried to do. I tried to get in this format of first unknown, second unknown, third unknown, and then the constant, right? So let's type these equations into these boxes, right? If you have 4 equations with 4 unknowns, you tell it to put more in there. But what are the coefficients on I1, I2, and I3 in this first equation? They are all 1. 1, 1, and -1, right? And then they equal 0. Okay. My second equation, read them off to me. -30, -41, 0, because there's no I3 in that. We did this wrong. I2 is 0. Right? I1 is -30. I2 is not here, so it's 0. I3 is -41. And then what's the constant? -45. And I come in, I do, okay, -30 again. Now it's 11. Now it's 0. And then I've got 80. All right, so I've just given the solver the coefficients. And I say solve the system, okay? And because it's a math website, it'll give you these strange constants, okay? But you can see here, I kind of like this because what it does is it shows me the equations that it interpreted, right? And sure enough, that's what they are, right? Those of you that take Math 17, you're like, yeah, just do the matrix and do the thing. Yeah, you're right. That's exactly what this thing did, right? But then it gave me the answer. So x would be I1, whatever this number turns out to be. And I got them written down, okay?
-1.38.
Right. Okay, so I've got the, is it 1.38? Yeah. Well, then I wrote this down wrong. Or did I type it in wrong? What did you get for I2? And then I wrote these down wrong. What was I1?
-1.384.
Amps. I2 was?
3.495.
And I3?
2.11.
Thank you. And how do I know they're all amps? Because it's current. That's what I've been solving for. And I put voltages and ohms in everything, right? So let's get back to my screen. Oh, I hit the wrong button. Try again. Change, not stop mirroring. Change. And then we'll go back to that. And this is so awkward. Hooray, hooray. Where's my mouse? There we go. Why is my screen not updating correctly? There we go. My recording wasn't doing right. Okay, so What happened here? How do we get from here to here? Linear solver Google. Right? We put it into a linear solver and it spat those things out. What do we learn from them? First of all, my I1. What went wrong? The direction. It has a negative sign on it, right? Currents can't be negative, so that means that I1 must be going the other way, right? But that's okay. We weren't asking about directions. I just wanted to know what the currents were, right? I2 and I3 were both correct. No surprise. All right. So that's cool. And then we got the currents for the other ones. Why would anybody put a circuit together like this, right? Where we've got like currents flowing the way they do and then things going backwards and blah, 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 blah. Where would another voltage maybe show up? Remember, voltages aren't just batteries. A voltage is any like positive source of energy in a circuit. So what if this were a solar panel connected to a rechargeable battery, right? That was also connected to a load, right? So we could have like the load, we could have the battery and maybe its own internal resistance or something, or maybe another thing that's in series with the battery always. But then we also have this solar panel, right? That's supplying voltage to the battery while simultaneously allowing the load to work, right? Your iPhone charger or whatever is going on, right? So that's one possibility. If we had current flowing backwards through one of these batteries, we would have a recharging circuit, right? Where we're sending current back into the battery to try and alter the chemistry of it. So there's lots of situations where you'll have multiple voltage sources. The graphics card company NVIDIA is finding this out, unfortunately, again. They had the problem in their 4000 series and now their 5000 series cards where they're using connectors with multiple voltage inputs, and then they're trying to put them together on the same buses, and it's melting wires and burning people's video cards. Why did they do it? Money. Yeah, I'm sure engineers went, you can't do this, and then some manager somewhere said, well, you are. Apparently the 5090 is pulling like 70 amps over a wire that's only designed for 15 or 25 amps or something like that.
They're barely going up in performance either.
Yeah.
That sounds like Boeing.
Yeah, no, it's what happens in a company when you prioritize profits over anything else. It's exactly what happens. And if you want to know more about politics, do you know who Pat Gelsinger is? He was the CEO of Intel. He is an engineer that became the CEO of Intel and was there as Intel grew in popularity. They fired him 2 weeks ago. Why? Because Intel isn't making enough money. And the last round of Intel chips was pretty bad. I blame AI. AI is sucking up all of the oxygen in the room when it comes to computer parts right now.
AMD seems to pick up the slack waste a little bit.
Yeah, except AMD can't market anything to save their lives. right, okay, yeah, good. I'm glad you asked the question. That's the most important one in the room, right? What are we going to do on an exam, Mr. Balogh, right? I can do this on my homework. I can't do it on my exam. I would love to be able to give you exams that are like fully online and all that baloney, but we can't. We don't have the logistics here to lock down the browsers and do all that baloney. So, and I'm not going to install spyware on your computers just so I can watch you take an exam. Talk about invasion of privacy. What I do for exams is if I gave you a problem where I'm requiring you to set it up and solve the equations, which I probably won't do, 70 minutes, 7 questions, that's more like a 20 to 25 minute problem, okay? if I did that, I would give you one of the unknown currents, so this became like a 2 equation, 2 unknown type. And I expect you to be able to do 2 equation, 2 unknowns by paper really quickly. Should be able to do that within a couple minutes. So that's what I'd do if I was going to give you a full problem like that. I believe what I did, I got the topics list out to you, right? That wasn't a fever dream from the anesthesiologist. That means that I already wrote your exam, and I'm pretty darn sure that I did not do that to you. I split it up in the sense of, like, I want to know about Kirchhoff, like, what do you know about Kirchhoff's rules and Kirchhoff's laws? And like I demonstrated, is this problem correct? Or since you now have this circuit, write down the equations and solve them. And I gave you really easy math to do, right? So I'm just seeing if you can like do those, but they're in separate problems so that it loads like a 10-minute problem and a 10-minute problem. Does that make sense? So pretty sure that's what I did. Ask me on Tuesday. What's happening Tuesday? We review for the exam, right? Where you come in with questions for me. But on your homework, I really don't care how you do this math. Use this website. You know, whatever your favorite linear solver is, whatever, if it's in your calculator, whatever, right? If you've never heard of a linear solver before, go back and watch what I just did, right? And that's how you will solve all of these problems without having to do all that horrible algebra. Do the horrible algebra. It's fine. It's fine. Electrical engineers have come up with many ways to get around this horrible algebra because it is bad. All right, I think it's time for a quiz. I already mentioned a little bit about household wiring. Let's just go over a few things. These are all of the surprised faces that exist in your house. Ooh. Right? Emojis are everywhere now. What's the mouth for? Ground. Okay. This is where you eat, right? This is where you put all the things. And then there's like a, I'm not sure if this is a teary eye or a droopy eye, right? I don't know what's going on. Right, but the two eyes, one's bigger, one's smaller, right? Okay. So typical wiring, the neutral wire, okay, which is like a reference wire, is connected to the bigger side. And then the hot wire is connected to the smaller side. This is what's referred to as a polarized plug. Most houses nowadays have polarized plugs in them. You really got to go looking for a house that's got the old-fashioned non-polarized plugs in it. And even then, a lot of those have been rewired and changed. But the idea here is, right, that ground is completely independent of the other two wires and goes to where it says ground. Like it's literally the wires connected to a grounding post that's next to your house, or like sometimes they tie it into like a gas pipe or a water pipe that's running underground, but they'll literally connect it to the ground.
What happens if you flip the hot and the
Yeah,
wire?
let's talk about that, okay? Because that does happen, okay? And I don't want to embarrass him, but Invierno, have I got this right so far? Invierno is a journeyman electrician, so I've got to be careful about what I say. Apprentice electrician, sorry, apprentice. Apprentice electrician, the step before journeyman. So, all right. So here's the reason electricians exist. It's hard to get these things correct in the complexities of a modern household. Especially when you have situations, do any of you have like plug-in floor lamps or devices that are controlled by a switch on the wall? Okay. But that plug, so like the top one is for the lamp, but the bottom one stays on all the time? Okay, that's a different kind of wiring than the standard set of wiring. Some plugs are switched where both of the plugs are on the switch, and then you have none of them. And then you've got ceiling fans that have several different switches depending, like some ceiling fans have slow, medium, and fast. Those can be actual wires, or more lately, they're the controller inside the fan.
It's fine. I just replaced the switch for my ceiling fan that's on my wall.
Yeah.
Turned the
for my room, apparently that
Yeah,
wire
no,
is actually
it's-
connected to the bathroom
Exactly.
fuse.
Yeah.
So
Yeah.
I
Yeah.
shocked myself.
Yeah, it's good. It's fun,
Cross
isn't it?
neutral.
Yeah,
And
this is why you hire electricians.
well,
So
I was like, why is the wire?
yeah. So the thing is with plugs, outlets nowadays, okay, is some of them have like 9 connections on the back, okay? And then there's little pieces of jumper wire. You can't really see it in this picture very well. It's sitting like right there. There's a little piece of, do you see how the copper connects this one to this one? You can break that piece of copper and it becomes one of those outlets that's like switched one way versus the other way. With like, and this doesn't even show you like what's on the back, okay? But there's the black wire going into one side on the back. There's the white wire coming over here, and then there's the ground wire. And then there'll be holes on the back sometimes where you can just slide the wires in after you strip them. There's so many ways this can go wrong, okay? That it's no surprise that electricians exist. And even new homes that electricians have blitzed through, especially in like in tract housing where a lot of the houses are kind of exactly the same. After you've done the same sort of wiring over and over again, it can get really easy to kind of zone out and get it backwards, okay? And so what does happen when you get something backwards? Well, the good news is that there's safety in place for this, right? Because with a polarized plug, a lot of modern appliances that have the polarized plug and the polarized outlet, they're expecting a certain polarization to keep you safe when you plug that device in. And if it's backwards, you can actually be exposed to some lethal amounts of electrical current. So that's why we have circuit breakers. This is one of the reasons circuit breakers exist. But as you can see in this wiring diagram, right, you might have switches and devices, okay? Like these could be your refrigerator. Hopefully it's not on a switch. But it could be like your coffee maker. This could be a floor lamp. This is your TV, whatever, right? They're on these switches. They only work when the switch is closed. But you see how they're all in parallel? So you don't, like in your kitchen, you don't want to have the refrigerator going and the coffee pot going in order for the microwave to be working, right? That would be series connection. You want to be able to run them independently. But they're all connected together to a circuit breaker through the meter, right, coming from the line from the outside. And that way, if one of these things, for whatever reason, gets plugged in wrong, is wired incorrectly, you do something funny as a homeowner, the circuit breaker will recognize the fact that there's too much current flowing in that branch and will shut itself off, right? Without shutting down the rest of the house, okay, ideally. So that's one of the safety mechanisms that's there. You go down to the hardware store. I did this when I bought my house, and I bought like a little $2 device that just plugs into the outlet, and it lights up with some LEDs that tell me, like, is it rewired in reverse? Is it ground, is the ground faulty? Are the hot and ground reversed? That's a pretty bad one, okay? And especially because I do all my own wiring. I always check. I've been changing out the outlets in my house over the last several years as my house has aged. They get kind of floppy and don't hold things in very well. The springs inside are going bad, and there's no good way to fix that. So there's ways to retension it, but you don't want to do that. Just replace it. It's like $1.50 at Lowe's to get a new outlet. And you turn the power off, follow the wiring exactly, but I have a little tester because I never trust myself to get it right. Ground wire I can get every single time. It's the other two I'm never quite sure about. So I wire it up, and then I turn it on and I test with my tester just to make sure I haven't done anything wrong. So it can get pretty difficult. I still don't understand what red wires do in my house because they seem to be connected to just about anything willy-nilly. And they're still, after 22 years of living in the same house, there are still switches that I don't know what they do. I flip them and nothing anywhere in the house goes on or off.
It's the neighbor's lights.
Must be. Or there's some external light outlet somewhere that I can't see because it's been buried by bushes or something, right? Like, I've been all over the place looking, trying to trace it up the wall with a special tracer, and I've never found it. Never found it. Anyway, So there are great mysteries to be had. And people like Invierno are doing, I'm telling you, electricians, plumbers, gods. Like, they are amazing at what they do. I've done both plumbing and electricity, not just in my own house, but at a family cabin. And oh my gosh, you can't pay electricians and plumbers enough for their knowledge. I thought quantum mechanics was hard until I got to lead piping, and then I was done. What was that? That's ground. Okay. Now, you may or may not have seen a plug that's a little bit like this one. Modern homes have a 4-pronged version of this, or a 3-pronged that looks slightly different. But these are 240-volt plugs for your dryer, or a hot water heater, or a stove, electric stove. They'll be plugged into your house. Actually has 240 volts coming to it, but the electricians at the panel will split that out to just 120-volt lines and then 240-volt lines, depending on what the circuit needs to have running on it. Some of your devices may not have a grounding plug, okay, and that's not a bad thing, but for certain devices it could be if there is a neutral hot swap somewhere in the device or in the circuit. This picture is trying to illustrate that if for some reason, like this electric drill is expecting the neutral to be connected to the case and the hot wire to the motor, if it's swapped and you hit the switch, you could be connecting yourself directly to the hot side. Without a ground wire, you become the path to the ground, okay? And that's where you'll get the shock. This doesn't happen very much anymore at all with polarized devices. With a ground wire in place as an extra safety, the ground wire is the fastest way to ground, the least resistance to ground. And so what would happen in this situation is the circuit breaker would probably trip, okay? And if the circuit breaker didn't trip, then another type of circuit breaker called a GCFI, GFCI? GCI? Which one is it? Just GFCI. You just call them GCs? Yeah, that's probably easier. A ground fault control interrupter, or a ground fault interrupter, or a ground control fault interrupter. I can never remember which way it goes. Basically, that device, if you have a plug in your house that's got test and reset on it, that's the GFI, okay? It's trying to sense a problem with ground and making sure the ground stays connected, okay? And so if it senses for some reason that there's some problem with ground, it'll trip. And it trips a whole bunch of lights or plugs that it might be connected to. By law, in modern homes, if you are within 4 feet, 6 feet? 6 feet of a water source, so a bathroom, the kitchen, right? You must have one of these plugs because water is a really quick way to ground. And if you drop your toaster in the bathtub, why would you have a toaster?
Every single one of my outlets by any water source does not have one of those.
Right.
And I kept telling my dad, I'm like,
Yeah.
you need to put them. He's like,
Okay, biologists, what's this? That's a neuron. Why are we talking about neurons? Well, I just had a bunch of my neurons neuroned. Why am I showing you a picture of a neuron? Down here, okay, at the nerve endings, okay, well, these are called dendrites, is that right? On either side? I can never remember. These will connect either to other neurons or will connect to nerve endings, like say in your fingers or something like that, right? So when you have a sensation of touch, right, and the proprioceptors in your fingers are going, ooh, fire off, right? They punch out an electrical charge. There's a whole bunch of stuff about potassium barrier. We're not going to get into that, right? But like electrical charges start to differentiate themselves at these nerve endings. And that signal propagates along a wire, the axon, right, all the way up to the nucleus of the cell where it gets processed. One way to describe you is you were a collection of electrical circuits powered by potassium pathways, right? and different cell potentials and things like that. Check me if I'm wrong, you anatomy and physiology geeks. Aren't there some neurons that are like up to almost a meter long in your body or something like that? Like they start in your brain and they go all the way down to like your bottom of your spinal cord or something like that, or down your arms or something. These are considered like single structures, right? In the body. Single cells, but not single cells, single structures. Single cell. Yeah, single structures made up of a bunch of cells. And there's a lot of stuff that can kind of go wrong. Ask me how I know. But particularly this sheath acting as an insulator around the axon, anyone who has multiple sclerosis has problems with this myelin sheath, okay? That sheath is degrading somehow, and the nerve electrical signals are being messed with either from outside or inside, and it causes problems in a person's ability to work and to move and to do things like that. But it is another electrical conduit, right? That can be grounded, that has potential across it. They're wired mostly in parallel, but there are some series connections in there. Especially, there's a lot of series connections in your brain, so maybe I should change that. Even though a lot of the series go into parallel. Neural networks are really complicated. Really complicated science to get through. I did not talk about RC circuits. I think I gave you, did I give you a homework problem with RC circuits in it? A resistor and a capacitor together?
No.
Did I take that out? I hope I was smart and took that out. We will get to this, I promise. But I'm going to save it for when we get to AC circuits, because there's more application to it in AC circuits. So we'll put that aside. Shouldn't have to worry about it. I did not put it on the exam, right? It wasn't a topic that I gave you, right?
No.
Yeah.
Is that unit 4?
Yeah, it'll be unit 4. Okay. So I apologize if I gave you a homework problem with it. If I did, let me know and I'll take it off.
Mr. Bale, is it resistor circuit analysis?
No. That's different. All right, have a fantastic weekend if I don't see you in grasp.